Okay, so let's take a look at the two special cases that you have with rational functions. First, we'll look at wholes. That's the case when denominator is 0. But in the case of a whole, the function will have a limit. It need not be defined at the limit point. That's part of the definition of limit. But it will always have a limit at the 0, even though it's not defined and it's not in the domain of the function. So that's what it means when we have a whole. And they're referred to as removable discontinuities because if the function were redefined at that one point, then in fact it would be continuous. So here are three different situations where we will have a hole in the graph. And the question is, you're given the rational function x minus 5 over x minus 5, and what does it equal? And of course, you know it's equal to 1. But it's not always equal to 1. It's equal to 1 if x doesn't equal 5. So what does it equal when x equals 5? Well, it is undefined when x equals 5. In other words, 5 is not in the domain of this rational function. The graph, of course, is going to reflect that. So here we have the point x equals 5, and here's the value 1, and it doesn't take the value 1 there, so there's a hole. On the other hand, it extends in both directions as the horizontal line, y equals 1, except that x equals 5. There's the hole. What about x minus 5 squared over x minus 5? What does it equal? Well, one of the x minus 5s upstairs is going to cancel with the one downstairs, and we're left with x minus 5. But once again, that works if x doesn't equal 5. On the other hand, if x does equal 5, it's going to be undefined when x equals 5. So what does that look like? So x minus 5 is the straight line. When x equals 0, the y value is minus 5, so it goes through that point. And when y is equal to 0, x would be equal to 5, except that there's a hole in the graph there because it doesn't take that value. Otherwise, it's the straight line with slope 45 degrees. And that would be the graph. So it's a graph with continuous everywhere except at 5. There's a hole there. Finally, the last example, x minus 5 cubed over x minus 5. So in that case, it's going to be x minus 5 squared if x doesn't equal 5. Otherwise, it's undefined. So what in the world does that graph look like? Well, this is a parabola. Where's the vertex? Well, the parabola vertex would ordinarily be at x equals 5. But it's not defined there, so there's a hole. And then the parabola goes up like this. So that gives you a feeling for what holes look like. Now let's take a look at a proof that the function x minus 5 over x minus 5 as x approaches 5, that's actually equal to 1. You know it from calculus days, but let's show using epsilon deltas exactly what the proof is going to look like. So according to the definition, for any epsilon greater than 0, there exists a delta greater than 0. If x minus 5 is less than delta, then x minus 5 over x minus 5 minus 1 is going to be less than epsilon. So that's what we have to prove. Working backwards, we take a look at this last inequality. That's the one that we need to work with to control x minus 5. And so as long as x doesn't equal 5, x minus 5 over itself is equal to 1. And 1 minus 1 is equal to 0. So the question is, what should delta be in order that 0 is less than epsilon? Well, this is probably the simplest limit proof you'll ever have, because you can choose any value for delta. Because the idea is that this function is essentially the same limit value everywhere nearby. And so we don't need to work hard to create a small interval. Delta could be a billion or a trillion or 1 billionth or 1 trillionth. Doesn't matter. So I just said, okay, take delta equals 1. In which case, if x satisfies the condition, and since x doesn't equal 5, we have exactly what it was that we need to have the proof. And that would conclude that proof. Okay, let's take a look at the other special case, that of an infinite discontinuity. There are really 4 possible ways in which you can have infinite discontinuities. The first graph over here illustrates having a vertical asymptote at positive infinity. The next graph shows having an infinite discontinuity at negative infinity. Well, it's actually at 0. The infinite discontinuity is negative. And then you can have different approaches for, in this case, y equals 1 over x. The graph is approaching positive infinity from the right, negative infinity from the left. And that's also another example of an infinite discontinuity. And of course, just taking minus that function will give you just the reverse of how you actually get to infinity. So those are the 4 possible cases you might encounter. We're going to just take a look at one case, the case of 1 over x squared. 1 over x squared as x goes to 0 is equal to infinity. We want to prove that. So here's the graph. We typically use a dashed line to indicate vertical asymptotic behavior. It's somewhat standard. And so the domain of this function is everything except 0. X can't be 0. So let's take a look at a proof. So we want to prove that the limit of 1 over x squared is equal to infinity. And the definition is that limit 1 over x squared is infinite if and only if. And now here, this is somewhat similar to the definitions that we had when we were talking about sequences, because we're going, you remember sequences were diverging to infinity. Well, this is a function that's going or diverging to infinity. For any m greater than 0, there exists a delta greater than 0, so that if x is sufficiently close to 0, namely within delta units, then 1 over x squared will be bigger than m. So the function has to be continuously getting bigger and bigger and bigger. So no matter how big the m is that we choose, we can always restrict this interval in such a way that 1 over x squared will be bigger than m. So the backwards scratch work. We're working with 1 over x squared bigger than m, and that implies cross multiplying 1 over m is bigger than x squared. And in turn, you can take the square roots and you have square root of x squared is absolute x. You want absolute x to be less than 1 over the square root of m. So what does the proof look like? Well, given m greater than 0, choose delta equal to 1 over the square root of m. No need to take 2 steps to determine delta. We just do it straightforward. And if 0 is less than absolute x minus 0 equals absolute x, is now going to equal the square root. This is the definition of absolute value. The square root of x squared is less than delta, which equals 1 over the square root of m. Squaring both sides, we have that x squared is less than 1 over m. And so, in turn, cross multiplying, we get the fact that 1 over x squared is bigger than m, which is what we needed to show. And that completes the proof that we wanted here.